I have talked about the graph of the basic sine function and the basic cosine function. So let's now focus on the graphing of the variations of sine or cosine functions. So suppose we consider a sine function. This is a certain variation. So that is, there's a number in front of the sine function. For example, this number I denoted with A. A can be positive or negative, right? So let's assume it's 2, simply a number 2. We know the graph of sine x. And if I multiply it by 2, how different the graph of the new function, yeah, compared to the basic sine function. Okay, with this, let's just draw one period of each function. Let's compare. So we use the 5 key points to sketch a function. So let's think of 5 points. When we sketch a basic sine function, here we just give x value, the function value, right? So that's a point, you see, x, y. And another x value and y value, the function value. You see, we just, for the sine x, the basic sine function, we have 5 key points. And then we just see that when x are these different 5 values, we get the y values, corresponding y values. And then the x, y, you see, we just show the 5 points, the ordered pair. And then we get the key feature of the sine curve. And by the way, we know the sine function at the first x, you get 0. And then 1. And 0, -1, 0. So then we connect those 5 points, we get sine curve. But look at the new function, which is y equals 2 times sine x. The difference is only like the number 2, right, appears. So this 2 has the effect. And if that's the y value without 2, and if you multiply each y by 2, then the y value will be twice of the previous y value. So then we see that this function, the function value will be twice of the previous function, the basic sine function. But 0 is not affected because twice of 0 is still 0. So that's still 0, but twice of 1 is 2, right? So whenever the function value is 0, then twice of 0 is not different. Yeah. So you see, twice of the -1 is -2. So then we can see for the new function, the y value will be twice as the old function, corresponding to the same x. So if we put these 5 points of the new function, here indicated in blue, so the x, y, you see that's a 0, 0, that's the one pair. X, y, right, that's another ordered pair. And the next pair, pi, 0. So then we just plot 5 key points, right? We get the xy coordinates of the 5 key points, then we can see the difference. So which one is sine curve? This one, the lower one. But actually this one is the sine, the basic sine curve. And which one's 2 times sine x? This black one. And we compare the 5 points. You see when the x-intercepts are still there, but the maximum value is, so all the other function values compared the sine with 2 times sine, and the differences at this, let's see. So this y value is twice as big as the basic sine function. But it is true for each y, right? So for each given x, so here this is the function, x versus y. And for each given x, if this is a sine x, and 2 times the sine x, is always twice of the sine x for whatever x. So that is why we got this stretched. Yeah, vertically stretched version. So we get the graph of 2 sine x. What if it's a half? But by the way, I want to introduce this one term. It is called amplitude. Amplitude of a periodic function is half the difference between the maximum and the minimum values of the function. So let's look at the function. So if we go back to the graph of the function, yeah, we'll go back to this graph of the function, and do we see for the basic sine function, the maximum value, the y value is 1. Minimum value is -1, right? So the difference will be 1 minus -1, which is 2. A half of that will be just 1. So the amplitude is 1. Yeah, so that is the definition of the amplitude. Let's look at what is the amplitude for this function, 2 sine x. Amplitude is 2. Yeah, so you can see the maximum displacement of the graph right from the horizontal line, the x-axis. So that is 2. And how do we calculate amplitude? It is just the largest function value of this given function, which is 2. The smallest function value, which is a -2. You see, largest minus the smallest, that's the difference. The difference, that means the largest and the smallest, they're 4 units apart. And then half of it, half of the difference will be half of 4, which is 2. So the 2 is defined to be the amplitude of the a function. This Okay, now we have seen that. And then let's look at another function. This is the same form. It's just a different number. So suppose the a value of a is half, right? Instead of 2, suppose we have half. Then what would be the picture of this function? So when it's half, let's still draw one period of the function. One period. So 5 key points. What are they? 5 key points. For the basic function, right, without half, imagine without half, we have the y value will be, suppose we don't have the half, the y value will be 0, 1, 0, -1, 0. But with half, then the y becomes half of each, right? Because without half, that means for the basic sine function, we have those values. Maximum 1, 0, -1, 0. Okay, so but then with a half, then each y will be multiplied by half. Then that's how we get, so 1 becomes half, -1 becomes -half. So we get, but 0 doesn't change, right? Half of 0 is still 0. So we have these ordered pairs. And then the 5 key points will become, you see the 0, 0, first pair, second pair, third, fourth, fifth. We have 5 points. Key points then will allow us to do a sketch of this. And we notice this 3 curves, and which one is the basic? The one in the middle. Yes, the one is this purplish that in the middle. So that is the basic function. And 2 sine x, that's the black function with amplitude 2. And half sine x will be the blue one with the amplitude half. You see the 3 functions, the largest function value for this half of sine x will be half. The smallest will be -half. So we can see from the table, that means, yeah, so using the 5 key points, we know the maximum for this function will be half. Minimum for that function will be -half. It happens at respectively half of pi and 3 pi over 2. So we can see this number a whenever we want to do a sketch of functions of this form. The a will affect the amplitude. So far we have tried different values of a when a is positive, right? So when a is bigger than 1, we notice a picture that is stretched vertically. When a is half, less than 1 case, so the amplitude of the curve is smaller. So now we can go to the Okay, so now let's look at another variation. Actually, we haven't seen the case when A is negative. What about this case? Suppose A is a negative number, such as -2. So if I want to graph y equals this, okay, A is -2, so I have a -2. It's this time negative. What happens is that just give the 5 key points. Suppose we look at the basic function, and it's very helpful when you look at the basic function. You see, right, basic function, the y will be 0, 1, 0, -1, and 0. So those are the function values for the basic sign over the 0 to 2 pi interval. You see from 0 to 2 pi, and those 5 key points. And when there is a coefficient times this y, so it will affect this y value for each given x, and the y will be multiplied by -2. So the positive becomes negative. Negative becomes positive because after you multiply the number by -2. So what we see is flipped. Yeah. Because we already know this, without negative sign, we have twice, right, height of that original basic function. But with a negative sign, that means the y will be opposite. Not only twice of that function, it's flipped. So that means we should look at this pair. So this is for this x, that's the y. So 0, 0, that's the first point for this function. And for the next x, at half of pi, this is the y, right? So then we get at half of pi, the y will be -2. And at pi, this is the y. So pi 0 at the another x, and the y value will be 2. So then we get five key points. We put x, y coordinates, and then let's draw the 5 ordered pairs, and then get a sketch, quick sketch. Okay, which one? So easily we can see that this is the basic function, right? So we can see that this is the basic function, and this is 2 times sine x, and this is -2 times sine x. And -2 sine x and +2 sine x, they have the same amplitude, because this -2 sine x looks the computation, the minimum is -2, maximum is still +2. So the difference between maximum and minimum is still 4. Half of the difference is still 2. So as we can see, the amplitude is simply is this number, absolute value of this number, which is 2 in this case. So let's say for any function in this form, a sine x, the amplitude, no matter what value a is, A can be positive or negative, right? So the amplitude of this function will be absolute value of A. Yeah, for example, when A is -2, so if we have a function that specifically -2 times sine x, then the amplitude is the absolute value of -2, which is 2. So as we can see, yeah, that's how far it is away from the largest distance from the x-axis. Okay, so the number A has the effect on the amplitude. When A is larger, that means when absolute value of A is larger, then the amplitude of the function is larger. So it's a quick summary here. The effect of A, when A is positive, this function is vertically stretched by a factor of A. When A is bigger than 1, right? You saw the case of 2, for example. It is vertically stretched a factor of 2. But if A is positive but less than 1, for example, half or 1/3, that means we can get that picture, the graph of this function by shrinking the basic function, vertically shrinking it by a factor of A. If it's half, you see we can shrink by a factor of half. If you have a negative A, then first just use positive and then get either stretched or shrink depending on the absolute value of A. And then later you do a reflection about the x-axis. Okay, now we're ready to look at another variation for sine. This time, then there's a number in the function that is here. Instead of sine x, we have sine number b, a value b times x. Then what will be the graph of this function? So let's assume b is positive. Since if you have a negative, for example, suppose I have a negative 3x, I want to graph this function, but it is the same as the negative sine 3x because the sine function is odd. We discussed even odd properties of each trigonometric function. So the sine function is odd. So sine of negative is negative of sine of something. So this, because of the odd property of sine, then that means we don't have to worry about the negative, because as long as we can take care of this sine with a positive number case, then later we can do a reflection, right? Do a reflection about x-axis. So we can always take care of we can get a graph of when the case, when this number b is negative. That's why we don't have to consider the case b when it's negative, because it can be converted into a case when b is positive. Yeah, then later do a reflection. That will allow us to find the picture for for the case when b is negative. So let's focus on the case when b is positive. So let's look at a concrete example. Here, b is a positive 2, but be careful, this 2 is not 2 here, right? It is a 2 in the sine function. So we want to graph the sine of 2x. Okay, so we want to still think of the 2x as a whole thing. We can treat this as t, for example, or you just name it whatever. That is a variable. Then as soon as I do a change of variable, then we can think of the basic sine function. Yeah. So let's just okay, do this basic function. So here you see the 2x as treated as one single quantity or variable. So this quantity versus the sine of this variable, that's just the basic function. If we look at this as a one variable, right? So it's a sine, the basic function of this variable. You can call it t, for example. So when this variable, using our 5 key points, just same 5 key points, when 2x is 0, half of pi, 3 pi over 2, 2 pi, and then the function value will be 0, 1, 0, negative 1, 0. Okay, so then we have 5 points. However, this versus the sine of this, we get 5 points. But right now, we want to graph x versus this y, not 2x versus this y. So if 2x is this, what is x? X should be half of this. So that's why we can see the x is half of each x. So when 2x is pi over 2, the x is half of that, which is pi over 4. When x is pi, then, I mean, that's 2x. When 2x is pi, then x will be half of pi. When 2x is 3 pi over 2, then x will be half of that. When 2x is 2 pi, then x will be pi, always half. So then that's how we get 5 key points. 5 key points. So only change to get x, right? So as half of that first row, yeah. Half of the entry in first row, then we get the x. Each x has the corresponding y, so the same y. Then we can see the x ranging from 0 to pi. Then let's do a sketch using these 5 points. After you plot the 5 points, you will see the right dots. You see the right dots indicating the 5 points. Here's one, there's another one. And we finish one complete cycle. So with that 5 points, we can see the blue, that we can do a sketch. You see in this window, you see one period of the sine 2x. So this 2 didn't affect the amplitude. It is in the sine function, and it affected the period because this is already one period, right? This one period is pi. You see from 0 to pi. So that is length of one period. And if you extend this period to the next interval, so from 0 to pi, you have one period. And then from pi to 2 pi, you get another period. You just reproduce the behavior. So from 0 to 2 pi, you see another period. So we see two periods of this function, y equals sine 2x. So compared to the basic sine function, and sine 2x has a smaller period. Its period is pi, not 2 pi. So we have, okay, we graphed over the same interval. You see from 0 to 2 pi, we see only one period of basic function, right? Just one period of basic function from here, from 0 to 2 pi. However, we can see two periods of this function, y equals sine 2x. Okay, so you can change numbers. You can change, for example, we're now looking at functions of this form, bx. What if b is half? So yes, we can try that. If b is half, so we still treat this whole thing as like input variable for sine, right? It's a basic sine function. So for basic sine function, so just think this quantity as one variable and sine of that variable. So that's the basic sine function. Basic sine function, we can use 5 key points, which is always the same 5 key points. So we have them listed here. And then for each, when half of x is 0, the sine of that input will be 0. When the input value, okay, well, let's call this half of x. It's half of pi, then the sine value will be 1. So you just do the same thing, except the writing is, this is input, and that is the corresponding output, right? So considering input variable as half of x. But right now we're trying to graph x versus y, not half of x versus y. So when half of x is 0, what is x? When half of x is a certain value, whatever value it is, then the x must be twice of that value, right? So that means x can be easily figured out. So let's see, when half of x is this, x must be twice of that. When half of x is this one, and then x must be twice of that one, which is pi. When half of x is pi, x must be 2 pi. So the x is twice of half of x. Yeah, easy to figure out. So then we get x, and for each x, the corresponding y is already found, right? Here. So corresponding y will be listed as well. So this each y here, each y for the to match that each x. And then we have 5 key points. And then let's use these 5 key points. And we notice the x range will be from 0 to 4 pi this time. You see, from 0 to 4 pi to complete one cycle of this function. So let's see this is one period. So the effect of half, right? Right now the function is sine half x. Its period is 4 pi. Yeah, compared to the basic function, the period is larger. Yeah, because basic sine x function has a period 2 pi. Okay, so now I want to give you a formula, actually, which is true for the function of this form sine bx. The period of this function is actually 2 pi over b. You notice earlier when we have this b, when b is 2, right? What is the, let's apply that. When we had sine 2x, the period is 2 pi over 2, which is pi. Yeah. When we now have the sine half of x, what's the period? Period is 4 pi. Why? Because we use the formula 2 pi over half. See, according to the formula, whatever the b value is, we just 2 pi divided by this b, right? Now, half. Divide half is the same as multiplying by 2. So 2 pi divide half. So 2 pi times reciprocal of half, which is 2. So 4 pi. That's why, yeah. So this formula, just remember, so that means you can see this b, different b corresponding to different period. Yeah, different b will correspond to different period. So the larger the b, the smaller the period. Like we have a 2, right? The period becomes smaller. But if b is half, smaller b, the corresponding to a larger period. So we notice the effect on the period. The graph is either stretched horizontally or compressed. Yeah. And now another variation is we try to graph, in addition to a and b at different spots of the function, then we can introduce another parameter that is c. So if you have a number c somewhere here, so let's consider functions of this form. Function of this form, let's try a specific value c. In this example, immediately you can see a, which is the scalar multiple of the sine function, it is 3. And b, which is in front of x and inside, yeah, this parenthesis, the b is 2. And c value is pi, is the number pi, which is, right, a real number. So now how do we graph one complete cycle of this curve? And we can, again, use the 5 key points. It's just that we have to use the basic sine function, the 5 key points of the basic sine function, and then we can graph it. And also we can think of the transformation or the shifting, for example, translation we look at this function, compare it with, I just rewrite the function by factoring 2. And then the x minus, that means x, if you factor out 2, which is this, right? This, do you see why? Because 2 is out, that means this will become half of the quantity pi. So, but you can double check if you want. You can always see like 2x times this 2 times half of pi, which is pi, right? So this you get back 2x minus pi. Yes, that's okay. We just rewrite, because after rewriting it, so we can see that this function is actually a translation of this function. Let's get the right sine. Suppose I have only just 2x. So this variable, we replace it with 2x only. So if I can graph this function, we know we can, right? Based on our current discussion. Yeah, so A is 3, B is 2. Yeah, like we can produce a graph like this. And then after we get this function, what do? We do a horizontal shift of half of pi units to the right. Then we will be able to get the blue function. Yeah, so you see, in order to get a graph of this function, one period of that function, we can graph one period of the function in pink. And then we do a shift, horizontal shift of half of pi units. So I mentioned the a version which is with both A and B. So if you run into this one, what do you do? Yeah, we know this function has amplitude that is absolute value of A. We know this function has the period 2 pi over B, right? So this function, we can, we know the main features, because this function, its period is determined by B. Its amplitude is determined by A. So just that's the important information that we can know from the given form. So we can look at, and then function of this form, then we can so that means to graph this function, we want to graph 3 sine 2x. Yeah, that means this quantity, let's replace it with x. And then we get that this is function looks simpler, right? We know its amplitude is 3. Amplitude is 3. Its period is what? 2 pi over 2, which is pi. So 3 and pi. So let's give a sketch of this function. You will see. Yeah, from 0 to pi, right? That's one period, as we can see here. Yeah, so this is one period of the function 3 sine 2x. However, we want to give a picture of that function using the sketch we already have. But all we need is to shift, right? Because this x is now replaced by what? X minus half of pi, right? So after we factor out, so this is actually sine, like 3, yeah. So we need to look at the x in the original, in the purple sketch, and now the x has become x minus half of pi. So that means using the purple sketch, if we shift that graph half of pi units to the right, we will be able to get this picture. So this is what we are doing. So yeah, just shift half of pi units. See, initially, okay, from here, then now here. Yeah, every point will be shifted half of pi units, right? So then we get one complete cycle of the graph we are looking for. So once you get a complete cycle, you see this picture, this problem has the same period, right? Still, the period is still, it's just after horizontal shift doesn't affect the period. The period is still pi. See this over this interval, that's still pi. From here to here, the length is pi. So the period is pi, still, yeah, just determined by this number. And the amplitude is still 3. Yeah, that doesn't change. So the amplitude and period, and it's just a horizontal shift. So once you get one period, you can get many periods, right? You can just extend the picture to the left, to the right, then you can see more periods of the blue curve. So after we get this, then one more example is that what if it's a plus? The plus sign here, okay, that's the only difference. So what we do, yes, in general, we define phase shift as in this formula. You see with a minus sign here, with a minus sign, and because we can factor out the b, then the number b, then we are left with this, right? So just like in the previous example, here is a pi, when the b is 2, right? We factor out the 2, then this is pi over 2. Yeah, so but we can always do that as long as c is non-zero, right? We can always factor out this number b, and then we get this form. And this number is called phase shift. Phase shift. You see when this quantity, yeah, we compare it with a sine bx, and this one is a sine b x minus c over b. So we already know the two pictures differ, right? Differ by this horizontal shift of this many units. To understand why, it's just you see whenever x equals this number, c over b. By the way, when x equals c over b, yes, and here when x is 0, right? This quantity is equivalent to this x is 0. That's when they have the same y. So that's this x equals c over b is equivalent to this function equal when this x is 0. So that's why they're related. So it's as if when this is 0, y is also 0. That origin, right? That's the origin. So that origin is when this x is c over b, then the y is also 0. So, but this is like this point is moved to this point. Yeah, that shows a horizontal shift. That is a point on this curve. So that's the horizontal shift of this many units to the right, because here we consider C and B, suppose they are just real numbers or positive numbers. But in case you have, you can always write into that form, because phase shift, the C does not have to be positive. Because when C is negative, we can still write the problem into this form. Okay, so here is the one case. We see a C which is pi, positive. Can we write into 3 sine 2 x? If I want to write it into negative, then just write negative minus negative pi, right? Because minus negative is plus pi. Yeah, so it's very easy to write this into that form. So now it's the minus sign, because we're looking at a general form. So we consider the group of functions that is in this form. The form is a, which is a number, a sine b x minus c, right? In case you have a plus certain value c, you can always write it as a. So this is our the form that is under consideration. So in case you have anything not in minus sign, you can always put it in the minus. Okay, so after we put it in minus, then what do we do? Then, yes, just like this problem. So we see the after we factor out the 2, right? And then we can write as x minus a number. Okay, with that, then we know the phase shift is negative half of pi. So that means if we produce graph of this function, sine 2x, that means instead of the whole thing becomes x, we consider this function. Then after we get graph of this function, then we do a horizontal shift to the left-hand side for half of pi units. Then we will get the desired function, this function, which is the same as the given function. So the phase shift is the number which is this number once you can write it into that form to fit the form. Yeah, so this is the phase shift. It's by definition, right? This suppose the given function can be written into a sine b times x minus certain number, c over b. And this number, be careful, it's a minus. Yeah, you have to write it into minus according to our definition. If you write into this form, then this number is called phase shift. Yeah. So I can give you another example. It's just y equals, let's say y equals 10 sine and like a 5x minus 3. Then what is the phase shift? The phase shift will be 3, right? So it's just exactly by definition. Then that's how we defined the phase shift. So the 3 is in the spot where we call phase shift. So that's the number. Okay, so far we have graphed different situations of a sine function, and then we different variations and covered almost all cases except for this case. So suppose you can do all this, and suppose I can still add a number. What does this do? So this number d, if d is not 0, that's going to affect the y, the function value, right? So that means if you know how to graph this part, then the d will, you are adding this many units to this quantity. That means the function, the y value will be either increased or decreased depending on the d. If d is positive, then the y will be higher, right? If d is negative, then y will be lower. So that's very intuitive, very easy to understand. So let's look at a picture. So we know how to get this part. We get, you see the dotted line, right? After we get this one period, okay, from the previous sketch, we get it. And then now if I add the number 1, then how do I get this variation? So what we get will be, with that function, you just elevate that plot upward for 1 unit. Yeah, so so you see this dotted line, I elevated 1 unit upward. Yeah, so just same shape, just at a different location. It is a curve 1 unit higher because each y for this function, right, is 1 unit higher than the other function. Yeah, so that is how we get the relative position to compare this. You see, because the other function is only this portion. You see, the dotted line is only this portion. And this solid blue line is, compared to the dotted line, is 1 unit higher, up. Yeah. So, and if 1 is negative, if you minus 1 instead of plus 1, then you can predict the resulting curve will be 1 unit lower than the dotted line. So it depends on this. So if I change it to -2 instead of +1, so that will be this function -2, what happens? After you get the dotted line, which is this part, 3 sine of 2x minus pi, after you get the dotted line, if we want to get the graph of 3 sine 2x minus pi minus 2, then we have to lower that dotted line 2 units downward. So yes, the effect of this number d, when d is positive, after you produce this function, you move that portion upward by d units. When d is negative, then your approach is to produce this function first, right, without considering d. And then if d is negative, then after you produce this graph and then lower that function d units. So then you get the graph of this desired function. So now with this variations, so for this more general case, you see for this more general case, what is the amplitude? It is A. Amplitude is absolute value of A. What is the period? Period is 2 pi over B. And because with the horizontal shift or vertical shift caused by D, it doesn't change your amplitude because the shape, this C and D will change the position of the function. They will not change the amplitude or the period of the function, as we discussed. Okay, so very important things to remember. From the given function, you can calculate quickly the amplitude, period, and phase shift, right, from the given form.